regression in R. Linear regression is used to find a relationship between dependent and the independent variable. It is a kind of supervised learning where we give a function to build a model and predict the values. Simple linear regression, we can generalize the equation in a mathematical form, that is y equal to c plus m into x, wherein y is the estimated dependent variable, the variable whose value we need to find out or we need to predict. C is the constant or the intercept. M is the slope or regression coefficient. And X is the value of independent variables. So what is intercept? Intercept simply means the value of dependent variable when independent value is at 0. And slope, it is the effect of independent variable on the estimation of dependent variable's value. For example, how can we establish a regression? It is very simple. Let's take a simple example of weight and height of a woman. Whenever we are creating a function or a model to estimate the value of, to establish a regression model, we need a dependent variable and an independent variable. When we are talking about simple linear regression, it means there is only one independent variable by which we are going to find the value of our dependent variable. So I'm taking here the example of weight and height. So it is very easy to understand that when the height increases, correspondingly weight also increases. We are taking a data set that is inbuilt in R and it is called as women data set. In it, there is values of height and weight of women aged between 30 to 39. And to build a regression model, the steps are, there should be a experiment of gathering a sample of observed values of X and corresponding Y. So here we are talking about, we are taking a sample of observed values of height and their corresponding weight. Next, create a relationship model using the LM function in R. So in R, whenever we want to build a model, linear model, we use a function that is LM, and within brackets we give the data name and the formula for the model. Find the coefficients for the model created and create the mathematical equation using these. So the coefficients for the model will be the intercept and the slope value, and we can see how a mathematical equation can be formed with that. Get a summary of relationship model to know the average errors in prediction, also called residuals. So what we will do is we'll create a model, we'll predict values from that, and we'll check the summary of that model in order to know how significant our model is. Last is to predict the values. So we'll be creating a new data set of height and we'll predict the value of weight from that new data. For the function to predict the values is predict function. And after that, I'll be showing you how to plot the graph and know how, if the model is meeting our assumptions or not. So let's go to R and let's build the model. So I have already written the codes for you. So the data set that I'm using is women data set. As you can see, there is a data frame with 15 observations and 2 variables, that is height and weight, and the women are aged between 30 to 39. So let's check the value of women data set. So we can see there are 15 values of height and weight. You see, as height increases, weight also increases. To check this, what we'll do is we'll check the linearity by plotting them. And to plot the values, the function is plot. Within the bracket, I'll be giving the name of the data set, that is women, $height. So what I'm writing is, I want to first take the height in corresponding with weight. So my height is the X value and my weight is the Y value. Let's execute this command. So you can see there is a linearity in the graph. It can be seen by a diagonal line that is showing there is a linear relationship between height and weight. Next, we are going to build a model. So I'm taking a variable LM model and I'm giving the function LM, within which I have given weight, that is my dependent variable. So I am taking my dependent variable in relation to the independent variable. So in simple linear relationship, there is only one independent variable. Then I'm giving the name of the data. So it is women data set. So I have mentioned the name of the data set here. Let's execute this model. You can see in the environment also, my variable has been saved with name lm model. Let's check the details of this model. So if I directly execute the model, what I'll receive in my output is the value of intercept and height, that is slope. So the value here, what does this say is, if we check our mathematical equation, that is weight equal to a plus b into height, where a is the intercept and b is the slope. So if I put the values of intercept and slope here, what will be my equation is weight is equal to, the intercept value is minus 87.52 plus slope is 3.45 and multiplied by height. So what it interprets is, the slope tells us there will be 4.545 times effect of height when we predict the value of weight, and intercept, it shows that how much is the value of dependent variable when the independent variable is at zero level. So if there is no height, there will be no weight. Next, let's check the summary of model in order to check its significance. Now, when we are checking the significance of a model, it is very important to check 5 factors. These are residuals, coefficients, then there is significance code, residual standard error, multiple r squared, adjusted r squared, and p-value. Let's start with residuals. What are residuals? They are the standard errors that occur when there is a difference in the values, like between the actual observed values and the response values the model predicts. So we can see there is a range in the errors. So the residual shows that there should be a symmetrical distribution across these points on the mean value of 0. Certain points are far away from the actual points. We'll plot these residuals and we'll see if it's meet our assumption for the linear regression or not later on. Next is coefficients. Coefficients, as I have already discussed, intercept and the slope value. So here it is important to understand that my independent variable was height. Now what are these factors that are showing are, first, estimated standard error. So it shows the slope value, that is 3.45, that this much effect, 3.45 times effect will be there on the weight of the women when height increases, or whatever the value of will be height, correspondingly there will be 3.5 times effect on the weight. Next is the t value. T value shows the variation in the range of the height and weight. Next is the p value, that is 1.09 e minus 14. What it shows is, p value is very essential to understand in a model, as p value tells you if your model is built significantly or not. It should be all less than 0.5. Whenever you are building a model, it tells that your model is significant. So there are two kind of p-values. One is for the factor and second is for whole model. Both should be less than 0.05 in order to make it significant. Next is the significance code. So as you can see here, they have given the list of significance code. What it tells is, if there are 3 stars, it shows it is the most significant factor in that model. 2 stars shows it is less than the other factors. Similarly, we can understand the other points. And if it is not at all significant, there will be no star in that factor. Next is residual standard error. So residual standard errors, they are the measure of the variation of observation around the regression line. So whenever we are building a model, when we plot the line, like we can see here, how much there is variation between the observations. If any of the observation is out of the line, we can understand through this value. Next is multiple R squared and adjusted R square. What it shows is, it shows how much accuracy of our model is, how well the model fits the actual values. It shows how much variation in dependent variable can be explained by the independent variable. As we can see here, there is 99% of the model variation. It helps to make the output. So we can see 99% of the independent variable, that is height. It helps in predicting the value of weight in our model. Then there is p-value, which I already told you should be less than 0.05 in order to make it significant, and here we can see it is less than 0.05. If you want to see what is, it has been given in scientific measure. If you want to know what is the actual value of this is, you can see it is very less. It is very less than 0.05, which makes it significant here. Now what we'll do is, we'll create a regression line on the graph we have already plotted here. We'll make a line, and for that the command is AB line. Within the bracket, we can either give the model name. I have given the whole formula for that. You can also take the model name. Then I'm giving the color for the line, that is red, and line width I am taking as 1. You can change the line width, and I'm executing this command. So you can see there is a straight line, which shows there is a very positive linear relationship between height and weight in the data set that we got here. Next, what we are doing is, we are predicting the value of weight with a new data set of height. So let's first check the values of our women data set. What I'm doing is, I'm taking the range of height and weight. So you can see in our data set, the range is from, for weight it is 115 to 164, and for height it is 58 and 72. The numbers are between this. So I'm creating a new data frame. I'm saving it in new data. The command to create a data frame is data.frame, and within brackets I am taking the vector, that is height equal to, so I am taking range that is not in this range that we already have. So I have taken 50, 75, 80 and 85. Now let's execute this command. If you want to check what we have saved in this data, you can see I have 4 variables here. Now what I am doing is, I am giving the command predict in order to predict the values of weight with my new data. I am saving it in predict underscore weight, predict function within brackets, same model that we have created, comma, the new data that I have got just created right now. So let's execute this command and check the value of predict. So you can see, for 1, that was when my height was 50, the weight that I predicted is 84.98. Similarly, when it was 75, my weight is in 171. So you can see there is a linear relationship again. As my height increases, weight is also increasing. Now let's build diagnostic plots to check the assumptions of linear regressions, and for that the command is plot within brackets name of the model. What it will do is, it will give you a series of graphs that will help you understand the assumptions. So to check the diagnostic plots, what we'll do is, we'll execute the command plot within the brackets name of the model. Now you can see there is a point here which is saying hit return to see next plot. So what we'll do is, we'll just click enter, and now there will be a graph here. So what we can see is the first plot, that is residual versus fitted, which is the residual plot. What it shows a relationship between x and y, and it should be a linear relationship. So there should be a straight or a particular line, and there should be no pattern there. So we can see here it is forming a proper line in order to show the linearity. We'll press enter again and there will be our next graph, which is the normality graph or the QQ plot, which shows the quantile plot also. What it shows is for fixed value of x and y, that is the variables here, so it is height and weight, data is normally distributed. And how we can test that, how we can see that our data is normally distributed, it should follow a straight line or a diagonal line. So we can see here there is a straight line here which shows the data is normally distributed. If there was any absence, or if there was the data is not in normal distribution, there will be a deviation in the line. Again, we'll be hitting enter, and the next graph is homoscedasticity graph, that is the scale location graph. What it shows is, it shows the variance of residuals in our data is in the same is the same for any of the value of x. So we have already seen this when we predicted the values also, that the data, that the residuals or the error that we have got, they are spread equally along the range of predictor. How we can see it is in a good, so how can we see that there is a equal spread along the range? Is there should be either straight line or a particular line that should not deviate much, so that we know that our residuals are spread in a same manner. So we are again pressing enter, and our last graph is Cook's distance plot, which what it tells is the observations are independent of each other, and it also helps in identifying the more influencing values in our data. So we can see here there is a values 15, 14, which what actually means is the residual values of these observations, they influence our data much, and we should remove these values in order to make our model much more significant. But we can see there is a straight line also which tells the model is very much significant, and it helps in predicting our values of weight very significantly. So it was a very easy example of simple linear regression, and similarly we can predict the other models with other data sets also. Multilinear regression in R. Multilinear regression is used to find the relationship between a dependent and multiple independent variables. For example, dependent variable can be sales. So if we want to predict the value of sales, there can be multiple independent factors that can affect the value of sales. So multilinear regression helps to build a model between the dependent, that in our example was sales, and multiple independent factors which affect the value of sales. The mathematical equation that can be generalized is y equal to c plus m1 into x1 plus m2 into x2 and plus m3 into x3 and so on. So where y is the dependent variable or the variable whose value we want to predict, c is the constant or the intercept. What is an intercept? It is the value where the value of independent variable is 0. Next is the m, that is slope. What is slope? It affects the value of independent variable, how much it will affect the value of dependent variable. Next is x. X is the value of independent variable. So here there can be multiple independent factors. So we have taken x1, x2, x3 and so on. So I have already told you the intercept is simply the value of dependent variable when independent is at 0 level. Slope, it affects the value of independent variable on the estimation of dependent variable's value. So when we establish a regression model where there are multiple independent factors, we are taking a very simple example to show how can we build a regression model in R with the inbuilt model, inbuilt data set, that is empty cars, where we will predict the value of MPG, that is miles per gallon, on the basis of different independent variables that are known. So let's go to R and predict the values of MPG. First, let me tell you what is empty cars data set. So empty car data set, that is motor trend car road test, what it comprises of is 10 aspects of automobile design and performance of 32 automobiles. So it is a data frame with 32 observations on 11 variables. So those 11 variables are MPG, cylinders, number of cylinders, then displacement, horsepower, axle ratio, weight, what is the cusic, that is the time, miles time, engine, transmission, whether it is automatic or manual, then number of gears and number of carburetors. What we'll do is first, what we are doing is we are creating a simple multiple linear regression model. Then we'll check how can we split the data and test the data with the already built data. Let me show you. So first we will be directly building a model like we did in simple linear regression. Then secondly, I'll tell you how to split the data and then create a model. First, what we are taking in independent variables are horsepower and weight. So I am plotting the data. I am plotting MPG with respect to horsepower. So to plot the graph, the command is plot. Within the bracket, first is the dependent variable in reference to the independent variable, comma, the name of the data set. Let's execute this command. And what we can see is as horsepower is increasing, MPG is going down. So there is a negative relationship. Next is weight. Same, it is the same relationship. When weight increases, MPG goes down. Now I am building a model. I am saving the values in a variable called result. It is the same way we created simple linear model. The formula is same, LM. Within the bracket, it is the dependent variable, that is MPG, the variable we want to predict in relation to horsepower plus means we are adding one more factor for predicting the value of MPG. So we are taking horsepower and weight, comma, the name of the data set. Let's execute this command and let's check the summary of this model. Now what we can see is both horsepower and weight is significant as their value is less than 0.05, that is p value, and also we have 2 stars and 3 stars with the factors. Now how do we get that these factors should be taken or not? We can also see there is r squared values. Whenever we are taking multiple linear regression, what we should always prefer adjusted r square. And one more factor is there, that is what r square does is it always increases whenever the variables are increasing. It should increase. It shows that our model is significant and giving a significant outcome. What adjusted r square does is adjusted r square adjusts the number of factors considered while predicting the value. So the value should increase, and adjusted r square always adjusts the number of variables and gives a significant outcome. Next, we can see p value is also less than 0.05, which means the model is significant. Now what we will do is we'll checking the multiple collinearity. First, we'll be splitting the data. So what is the use of splitting the data? We are dealing with very small data here, but data can be very large. So it is very helpful to build a data and test the data from same data set. When we divide the data into training and test data set, what we will do is we'll build our model on training data set and we'll test the value of outcome with test data set. So how to split the data? The command to split the data is what I am saving this split indices into training row index. So I am taking the command sample. So sample command will split the data as we have taken the probability as 0.8. So it will take the 80% of the data. How will it split is first I am giving how many rows are there. So 1 to n row of empty cars. So n row means the last row of the empty car till there. What I want is I want 80% of the data. I am taking the 80% of the data into this variable and it will take it randomly as I am taking the sample command. Out of those 32 rows, it will randomly take 80% of the data and it will transfer it to the variable training row index. After that, I am creating a variable training data. Now, out of this empty car data set, the 80% of the data will be transferred to training data set. I have taken the square bracket, which means empty car square bracket. That is, I am subsetting the data based on the training row index. That is 80% of the total data I want in training data set. Comma means all the columns but only 80% of the rows. Then remaining into test data. Test data, the variable name, and I am giving the name of the data set, that is empty cars. Again square brackets, I am subsetting the data minus training row index. What does it mean is all the remaining rows which were not taken in the training data should be taken in test data. Let's execute this command also. Now let's create the model. Now I'm building the model on training data set and will be testing the data and testing the model with the training data test data set. So we will be building the model on training data set and testing our model with the test data set. To build the model, I am taking 4 variables, that is cylinder, displacement, horsepower and weight. So let's build this model and let's check the summary of this model. So what you can see here is, let's check the coefficients first. It will help us to know whether the factors are significant for our model or not. So as you can see, there are 3 stars with weight, which means weight is a very significant factor in order to predict the value of MPG, but remaining cylinder, displacement and horsepower are with very less stars, very less significance code, which means they are less significant. Now how do we understand which factor to remove first? So we'll be removing them one by one based upon their p values. So what we know is p value should be less than 0.05. Now you can see there are 2 factors which a little bit significant, but you can see displacement is not at all significant in order to predict the value of MPG. So what I am doing is I am removing displacement from my model first. To remove the factor, what you can do is just comment that factors using a hash key. Now again execute the command. This time it will only take cylinder, horsepower and weight, and let's check the summary again. Also in the earlier model which we created with displacement, you can see the multiple r square and r adjusted r square is 0.8408, around 84% or 86% accuracy is there. What it tells is 86% of the data is helping us to predict the value of MPG. Now what we want is this value should either increase or it should give a positive result in order to get a significant model and better predictions. So our next model that we created is with cylinder, horsepower, weight, and we are predicting the value of MPG. Let's check its summary. So now the other factors, that is cylinder and horsepower, they have there is no stars here, but one of the factors should be significant enough in order to predict the values. You can see our r squared value has improved, has gone down. So what you can see is we have removed displacement from our model and the value of the factors has changed. There are the p value of cylinders and horsepower has increased, but we will be removing the cylinder first because it is higher in the p value. So let's remove the value of p value related to cylinder. Execute the model again. Now what you can see is both horsepower and weight has become significant for the prediction of MPG value. Both values have p value less than 0.05 and r squared of the model has also improved. So what it is saying is 83% of our model, data of our model helps to predict the value of MPG, and the p value of model is very less. It is very less than 0.05, which shows now the model is significant to predict the values. Now how do we check if our data, if our model is giving good result? They are predicting correct values. So we will be testing it with the help of test data. I am saving the values in the variable test data $mpg pred. What it means is in test data variable I am adding a column that is mpg pred, and I am saving the values of predicted values from the model. Now let's execute this command. Within the predict function I am giving the model name, and after that the test data that we created earlier. You can see what I have done is I have only executed test data here. So it has given me the values that are present in variable test data, and I will be adding a column here with the name mpg pred, within which the value of prediction will be saved. Now let's execute this command and check the table. Now you can see what we have done is there is mpg column here and there is predicted value of mpg. The actual value that the data set was having is 21.4 for Hornet 4 drive. That is the name of the car, and my prediction for this mpg is 21.19, which is more or less very near to it. Similarly, you can see there are two deviations, but otherwise the data is matching very nicely. So we can see our model is predicting correct values. Now, how to check if our model is accurate or not? How much there is deviation in our data? For that, there is MAPE calculation. MAPE, it means mean absolute percentage error. So we will be calculating the mean value of the errors that occurred during the prediction of values. For that, formula is we will be taking mean. So the formula is mean. Within the bracket, I am taking the absolute values. For that, the function is abs. It tells you that the values whichever will be resulting, it will be in absolute form. So I am subtracting the actual mpg values from the predicted values of mpg, dividing it by the original values, and I will be taking the mean of this whole formula. Let's execute this command and let's check the value of MAPE. So you can see MAPE is 0.14, which means there is 0.14 deviation in the values of predicted values. The lesser the value of MAPE, the better it is. It shows there will be less error in the prediction of our predicting variable. Now, how to check the assumptions? Whether the model is meeting our assumptions or not, we will be plotting diagnostic plots. The formula I have already we have discussed in simple linear regression also. It is plot within the bracket name of the model. So let's check the first graph. It is the residual plot. So you can see there is a relationship between the residuals and the fitted values. There is no deviated line here. There is a proper line formed in order to tell the relationship and the linearity between residuals and fitted values. Next, let's enter again, and there is normality graph, that is the QQ plot. So there is a straight line which tells us the data is normally distributed and follow a straight line. If there has been any absence of normality, the line should have been deviated. Next graph is scale location. We can see the line is more or less straight. It is in no deviation, and the data of residuals is spread equally along the line. There is a homoscedasticity in the data set. And the last graph, that is the residuals versus leverage or Cook's distance plot. It helps us to find out the values or observations that influence our data set. So we can see the values related to Toyota Corolla, Lincoln Continental, and Mercedes Bora. They are affecting the values of our data set. Uh, so the graph helps us to find out the observations that are influencing our model the most. So it is very easy to build a multiple linear regression model. What you have to do is you should always have a data set with proper linearity, normally distributed data, and whenever you build a model, check its accuracy, and summary of the model in order to predict your values properly. Logistic regression in R. Logistic regression is a classification algorithm. So it is a function that weighs the input feature or variable so that the output is separated one class to positive values and the other one into the negative values. So in other words, we can say logistic regression predicts a binary outcome, that is either 1 or 0, yes or no, true or false, given a set of independent variables. It is a special case of linear regression when the outcome variable is in categorical value. So logistic regression is also known as generalized linear model, which is the function name used in R, that is GLM. So as you can see in the picture also, we are giving different variables as in the model that we created, and the outcome is either happy or sad. So logistic regression helps us to get to a conclusion or a result where there is either a true or a false value. Some of the examples that can be taken for logistic regression are results of a cricket match. So we generally see a prediction rate on the screen when there is a cricket match, whether the team will win or not. So it is an example of logistic regression. Similarly, if a customer will churn or not after availing a service or buying a product, or another example can be a student selection for a specific course or a college, provided some of the variables or factors. As you can see in today's time, in online courses, people generally take some information regarding students' earlier results and grades and colleges. So it helps in selection rate of that student for that course. So when we build a model, there are different points, we can say elements, that we should understand in order to predict a good model, to create a good model. First is the variables that are required. So we need to understand which variables are helping our model for predicting a better values. We should understand that we should not use a large number of variables, because it will make our model complex. A model will be a better model if we use less variables but significant variables to our model. Next is significance codes. They help us to understand the importance of variables. So as we also discussed in linear regression models, that significance code help us to understand which variables are important for the model, or which variable are affecting the predicting value of that model. Next is the p-value. So p-value is a basic and important factor to understand whether the variable is better for our model or not. So p-value should always be less than 0.05 in order to be kept in that model. And last is AIC. So the Akai information criterion. So it is a estimate of prediction errors. So it helps us to statistically give the quality of the model, whether it is a good model or not. It should be less in the value. Whenever the AIC value is less, it says that the model built is a good model. So as you can see, AIC estimates the quality of each model relative to each of the other models. So when we are creating models, we will not get it at once. We have to create multiple models in order to get to the best model. So AIC helps us to estimate the quality of each model. Lower AIC means model is considered to be closer to the truth. So lower the AIC, it means the value that came out, and the result that are coming. Lower AIC means that the prediction that is resulting in from our model is of better quality. To use AIC for model selection, we simply choose the model given over the set of model considered. So AIC models is used to select the model over different models when the value of AIC is less. Next is confusion matrix. So confusion matrix is used in order to summarize the prediction result and get the accuracy of our model. So it is nothing but a tabular representation of actual versus predicted values. It is also known as error matrix. It is the summary of prediction result on a classification problem. The number of correct and incorrect predictions are summarized with the count values and broken down by each value. So as you can see in the image also, so there are total number of observations were 165. So we have built a model and predicted the values. So it is a tabular representation comparing the actual and the predicted results. So the first one, the where it is 50 value, so it is actually the result should be no, and our prediction also says no. So there are 50 values which have the same result. There are 10 values and where actually it was no and we predicted yes. Similarly, where there is actually there was yes but predicted no, there are 5 values. And if we the actual was no and predicted yes, there were 100 values. So in total, it becomes 165. So it shows a matrix uh, showing summary of our actual and predicted results. Comparison of that. So let's go to R and create a logistic regression model. So first we will read the data. So we are taking the data from the URL. It is available online. So the data is about the selection of students. We are given with the GRE values. So the data shows GRE values, that is graduate record exam score, and GPA, grade point average, and prestige of undergraduate institutions. So how it will affect the admission of a student into a graduate school. So let's check the variables saved in this data. So you can see there are 4 columns, that is 4 variables. First is the admit variable, that whether based upon these factors a student has been selected or not for the graduate school. Next is the GRE value and GPA value and the rank of the institution. How does it affect the admission? We will build a model for that and we'll check the result. So let's check the structure of this data. I am saving this data. I have saved this data in my data variable. And for checking the structure, the command is str. Str will help you to understand the data types and get the observations and variables of that data set. So there are total 400 observations and 4 variables. Admit is an integer value. As you can see, it is the data type of this vector is integer. Similarly, for GRE, it is integer, for GPA, numeric, and for rank, it is integer. And let's also check the summary of this data set. So you can see we are not getting the result properly because if you can check the admit is in 0 and 1 form. It is a binary form. And similarly, rank, it is also a categorical value. So we need to first apply, we have to convert them into factors so that we can easily get the data from that. So to convert any of the vector into a factor or a categorical value, the command for that is as.factor. So what we are doing is we are converting the data type into factor, and using $sign we can apply the command to a particular column of the data set. As in this, my data set is my data and I want to convert rank column into factor. So I have executed this command. Similarly for admit also. Now let's check the structure again. So you can see both the columns has been converted into factors. There are 2 levels here, that is 0 and 1. And here there are 4 levels, 1, 2, 3, 4. Now I am checking cross tab. So what does a cross tab? X tab means cross tab. So this command, what does it do is it will tell us which rank is more successful in getting the admissions. So you can see there were four ranks that are four colleges, 1, 2, 3, 4, and there are the result of the admissions here. So in first college, the students, there were 400 observations, as you can check there. So out of that 420 were not selected in one, 33 got selected in one, 54 got selected in two, 28. So they are the metrics, or you can say tabular representation, to know how the data has been split, the students, whether they got selected in which college or not. So we are creating a logistic regression model. For that, the command is GLM. The model is created in same way we created the regression models, like linear regression, multiple linear regression. So it is the same way. The command name here will be GLM, that is generalized linear model. I am saving my model in my logit variable. Inside the bracket, I am first giving the dependent variable. So we want to understand whether the student got admit or not in the college. So the first, the dependent variable is admit here, and these are the independent factors on which we will get the output. So GRE, GPA, and rank. Now data is my data and family. So you can check the GLM. Now let's create model. So we will be creating different models here. First model, it is directly on the whole data frame. The second model that we will be building, it will be after splitting the data into test and training data set. And third will be after checking the variables, which one is significant, which is not, and keeping only those variables that are significant. So first, let's build a model on all the independent variables and whole data set. So when we want to create a model, we use the function GLM. Inside that, inside the bracket, the first thing we mention is the dependent variable. In our case, it is the admit, that is the factor which will tell you whether the student is selected or not, that we are predicting. All the independent variables, then the name of the data frame and family. So if you want to know what is family here, what does it describe, you can always get help from R by questioning in GLM, and you will get a help here. You will get the whole formula and description of that formula. So we are checking family here. So family is a description of errors, error distribution, and link function to be used in the model. For GLM, this can be a character string naming a family function, resulting to call a family function. Let's see what are the different families that we can take. So family objects provide a convenient way to specify the details of the model used by the function GLM. So some of the models functions that we can use is binomial, gamma, Poison. It depends upon the type of data you are using. For now, as we are using a normal data frame and making a logical relationship, so for that we are using a binomial family function here. So let's execute the command and create the data. So let's execute the command and checking the summary of the model. So as discussed earlier, there are several elements that we need to understand when we are understanding the summary of the model. So first are the variables that we are keeping for our model, p-values, and the significance code and EIC value. So first, the variables that we used are GRE, GPA, and rank. So you can see there were four ranks, and we converted them to the factor data type. So every rank became a category here, and the significance code here, they can tell you how significant a variable is in our model. So rank 3 and rank 4 is the most significant variable, and other variables GRE, GP and rank 2 are less significant, but still they are significant for the prediction of model. And the AIC of this model is 470.5. So let's create one more model wherein we will be distributing the data into training and test data set, and let's check if there is any change in the AIC value of this model, and also if there is any change in the significance of the variables. So for dividing the data set into training and test, what we will be doing is using sample command. For that, first we will save all the rows of my data into a new variable, that is n, and after that I'll be using sample command and dividing the whole data set, that whole rows into a 70 into 30% of ratio. For that, the command is from first taking all the rows for 1 to n, that is 1 to the last number of this row, that here it is 400 rows. So 1 to 400, and that is n. And then we will give the size. So we are giving 70% of the whole data. And replace, we are taking it false because we want each and every record of this data set to be used. So we are not replacing any of the record for our 70% or 30% data. So let's execute this command. Now we are subsetting the data set, the whole my data set. So the first variable is train, that is for the training data set on which we will be building our model, and next variable will be for test, in which we will be predicting our values from the model we will be building. So for training data set, from the whole data, that is the name of my data frame, for subsetting I am using bracket notations, and within brackets I am specifying the list of rows that are saved in sample variable here, that are the 70% of the whole data set. Next, it is the test. So except the rows that are saved in training, the rest will be saved in test data set. I'm using a minus sign with sample here to eliminate all the rows that are saved in training data set. Now that I have created, divided and created different data sets for our model, we will be building a second model. So I am saving the model in log R1, again using the function glm. This time I will be using data set as train and execute the command. So let's check the summary of this model. Now you can see the AIC of the whole model has decreased, which means it is a better way to create a model. As we know, lesser the AIC, the better the model it will be. And now let's check the variables that we want to keep in our model or not. So here you can see GRE, it has become more significant, and rank 4 and rank 3 are also significant. Even rank 2 is significant because you can see there is dot here, which means it is a slightly significant variable. But GPA here, which is a insignificant factor, because the value of P here is more than 0.05, which is very, the value is very high here, 0.38. So we will be removing this value and will again build a model to get a significant prediction. Before that, what we can do is, as we have created a model here, let's also check the accuracy of this model and predict the values if this model gives us a better prediction, or if after removing a variable there will be better prediction. So for predicting, the command that will be used is predict. The command that is used for prediction is predict. I am saving those variables in predicted. Within the function predict, the first thing we mention is the model of the model that I have saved in log R1. So it is the model that I have created on training data set. Next, we will be mentioning new data. So new data here is the test data set that we have created. So what we have done is we are building a model on training data set and predicting it with test data set. And type here is response. So what is response? Let's again get help from R, and you can see what is predict whole tells you. So here you can see if you check predict, there is help, but there is a general help that we are getting. Below you can see there is predict.glm that we want here. So let's click it, and here is the formula that you will be using for predict. The most needed objects in this are first the data, the model that we created, the data frame that we are using, and then the type. So type can be of link, response, and terms. So how do we decide which to select? Here is the details for that. The type of prediction required. The default is on the scale of linear prediction. The alternative response is on the scale of response variable. Thus, the default binomial model and the detailed prediction are of log odds. So they are probabilities. Response gives the prediction probability. So what we want is, we want our response to be in the form of prediction, in the form of probabilities. So therefore we are taking response as a data type here, as a type for our prediction here. So we have executed the command. Now if you check the values of response prediction, so my variable is predicted. I'm printing the values. There are many values, so let's check the first 6 values. For that I'm using head command. So you can see it is a very high number with many decimal points. For that what we will do is, and we know that actual admit, the selection process, we were having a binary levels, that is 0 and 1. So we will be using the formula here, if else, wherein the predicted values, if they are greater than 0.5, it will print 0, otherwise it will print 1 to our predicted values. And I'm saving it in predict v variable, and I'm converting those values into factors so that we can get a summary out of it. Now after we have converted into factor and 0 and 1 form, let's check the values again, and you will be able to see the output. So you see the levels have been changed to 0 and 1 here. Now let's combine the variable with the column, predicted column, in our test data set, so that we know what we can compare actual and predicted values. For that I'm using cbind, giving the name of the data set and then the column, and let's check the values. So there is admit here, and then there is predicted values. So you can see there is some difference, like for first it is correct, actual was 0 and we predicted 0. That means it was the person was not selected here, and we predicted correctly. Then again it is correct that the student is selected, but after that there is a slight difference. So let's check the accuracy of this model. To check the accuracy of model, there is a library we can use for that, that is caret, C-A-R-E-T. You can either download it from packages, or what you can do is you can just write the command install.packages. It will install your package. Then you have to load it using library command. Then there is a function here as a confusion matrix. So confusion matrix, as we already discussed, is a tabular form which helps us to understand the accuracy of model. So within confusion matrix formula, the first thing we mention is the actual value. So the name of my data set was test, and I wanted admit, that is actual. Then there is the predicted values. So let's execute this command and let's see the output. So you can see there is a confusion matrix here. You can see there is 14 values in difference here and 26 values difference here. The accuracy level of this model is 66%, 66.67%. Now let's build one more model where we will be removing one of the variables from our model. So earlier, let's go to the summary again of the model we created and check which variable was significant, which one not. So according to our model, GPA was least significant. So the new model we will be building, in that we will be removing GPA factor. So I'm again splitting the data set, because in this we will be using test2 as a variable, because otherwise we will not be able to compare both the models. I'm only changing the test data set so that we can compare the earlier model predictions and the new model predictions. Now I have executed the commands and divided the dataset. Now I'm creating a new model wherein I have removed GPA because it was least important according to my earlier summary, and I'm using training dataset here. Let's execute this command and check the summary again. So earlier you can see in GRE all the factors have become the significant variables. The p values are also less than 0.05, so each of these variable is significant now. And AIC of this model, let's compare the earlier model and this model. The AIC of my earlier model was 333.15, now it is 334. So there is slight difference, just 1%, one value of very, they are almost same, and my all the factors have become significant. So it is a better option to keep only less those factors that are more effective, more important. Lesser the variables, better the prediction will be if they are all affecting the model in a positive way. Now let's predict the values using test2 dataset that we created just now. Again using predict command. Using predict command and dataset as test2, type will be response because we need a probability result. Now again I am using if-else command for converting the responses into a factor of 0 and 1 and combining it with test2 dataset. Let's check the result. Now again some of the result is matching and some there is difference for some result. Now let's check the accuracy. Now I'm using to check the accuracy we can use different functions. First I'm using again the confusion matrix. If you want to let's execute this command, you can see the accuracy of this model is 67%. Now you can see the accuracy of this model has come up to 70%, 70.83%. You can also see one way of creating data frame this confusion matrix was using confusion matrix command from package Caret. Other command that you can use is table command, wherein you will be giving the actual column, actual values that you want to check for, and comma the name of the variable wherein the predictions are saved and if they are greater than 0.5. So let's execute this command and you can see the table is again we can check the values, there are how many errors are there. And last function that you can use to check the accuracy is the mean. So we will be calculating mean for all the predictions which are equal to admit. Let's check. So you can see the accuracy here was 70.83 and our mean is also in the same probability mean value. So it tells us the accuracy of this model is 70.83%. Now we will be taking a new data frame, just two values, and we will be checking if we are getting a output or not from our model that we created here. So I am using GRE here because I have GRE and rank values in my model. So let's check the range of GRE. Why I'm checking the range of GRE when we are creating a new data frame that I'm creating here. It will be for predicting the values. So in my data frame, I'll be taking GRE value in between the range that I already have. If you take the value out of the range, it might not give you a successful answer or a good prediction because we have predicted or we have created the model for the values present in range present in our data frame. So if we take GRE as 700 and rank of the institution as 3, let's check the data frame. So this is my data frame. Now I'm predicting with my model that I have created after removing GPA from it. So the value is minus 0.59. If I'm using if else command and checking the value, so it comes out to be 0. So which means the student is not selected as per our prediction model. So you can use the prediction model in the way that your result is the model is giving a good accuracy with AIC value less, and each variable is significant for the model. Let's sum up the logistic regression. So we covered about logistic regression is the outcome is in categorical value, that whether the student will be selected or not. So it is a binary outcome. It is also known as generalized linear model, for which we use function GLM. Then examples of logistic regression were cricket match, that if the team will win or not, we see the prediction when we watch a match. Next is the customer will churn or not after availing the service or buying a product. Next is student selection, that we just did created a model for that. And next is the understanding the summary of a model. For understanding the elements that are important are variable requirement, significance code, p-values, and AIC. That lesser the AIC, the better it will be. You should know what is AIC. It estimates the quality of each model. Lesser the better, and it helps to select the smallest AIC, helps us to select the best model out of all the considered models. And confusion matrix, it is a tabular representation of actual versus predicted values. It is also known as error matrix. There are 3 different ways in which you can create a confusion matrix in R. So it is using caret package, where the command is confusion matrix, using table command, and using mean command.